The function f of z is said to be differentiable at z equals z0 if the limit as delta z tends towards 0 of f of z0 plus delta z minus f of z0 all divided by delta z exists. So here's the picture. We have some given complex number z0, and z0 plus delta z is a complex number that's close to z0. It can be anywhere close to z0. I could have shown it here or here or here. So this definition is very similar looking to the definition of the derivative of a real valued function at some value. Well, we're calling it z0 here, but if we're talking about a real valued function, we would replace z0 with, say, x0. Now, if we want the distance between the complex numbers, we first of all subtract the complex numbers. We say take this complex number and subtract z0. Well, that's just going to give us delta z. Then we get the modulus of delta z. To get the distance between these 2 points, of course, we just subtract the complex numbers and take the modulus. So, roughly speaking, we're getting the distance between these 2 points and dividing it by the distance between these 2 points. Although, in this definition here, we won't get a real number. In general, we get a complex number. Okay, if we were to divide the distances, we would, of course, just get a real number. Let's suppose that z0 is called x0 plus I y0. So x0 and y0 are fixed values for the real and imaginary parts of the complex number. If we're adding on delta z, well, we could think of that as adding delta x onto the real part of the complex number, and I times delta y is added onto the imaginary part of the complex number. So that's the same thing as adding on delta x plus I times delta y to the complex number z0. Now here we're getting the derivative of f of z at a particular value, z0. So we can write that with the familiar notation df dz at z equals z0, or f prime of z0. Now for this function fz to be differentiable at z0, this limit must exist and be independent of the path we use to take this limit. So we want the derivative at z0. We were using this point here, and when we take the limit as delta z goes to 0, it shouldn't matter which path we use in taking that limit. And of course it shouldn't matter where z0 plus delta z is. I could have taken z0 plus delta z to be this point here, and then delta z, well, the modulus of delta z would be the length of this line here. So it doesn't matter how we take the limit, where we start out from as we approach z0, and what path we take the limit along. A point at which the derivative does not exist is called a singular point of the function. A function f of z is said to be analytic at a point z0 if it is differentiable throughout a neighbourhood of z0, however small. A neighbourhood of z0 is the region contained within some circle. This should be z here. The modulus of z minus z0 equals r. So for example, if we want our function to be differentiable or analytic at z0, then we should be able to find a neighbourhood of z0, that is a circle centred at z0, such that the function is differentiable everywhere at all points inside the circle. So the limit that we saw must exist for all points within inside that circle. So the radius of this circle is the distance of any point on the circle to the centre. So if we call any point on the circle z, then the distance of z to z0, that is the modulus of z minus z0, equals r. So this would be the radius, r would be the radius of this neighbourhood. Here is an example of a function that is not continuous at the points plus I or minus I. Because if we plug plus I or minus I into this function, we get 1 divided by 0. So division by 0 is not defined, so the function is not continuous at z equals plus or minus I. If a function is discontinuous at a point, then it is not differentiable at that point. So the function is not differentiable at the points plus or minus I. So the function has singular points at the points plus or minus I. However, this function is differentiable everywhere else. So to get the derivative, we just apply this limit here, and if we calculate this limit, we know what we'll get. We'll get the same result that we would get by applying the quotient rule to a real function with z replaced by x. So if we're differentiating 1 over x squared plus 1 with respect to x, then we would get this here. That's because this limit has the same form as the limit as the derivative of a real valued function. Instead of using the quotient rule, we could write our function like this and use the chain rule. So we take the minus 1 in front, subtract 1 from minus 1 to get minus 2, then multiply by the derivative of what's inside, which is 2z. And we can write this as minus 2z over z squared plus 1 squared. So that's using the quotient rule or the chain rule. Of course, we could go through first principles, but this thing would take a while to work out using first principles. Now let's look at this example here. This function is discontinuous at z equals minus I, because at z equals minus I the denominator is 0. So the function is not even defined at z equals minus I. So if a function is not continuous at a point, then it's not differentiable at that point. The reason it's not differentiable is because the function is not even defined at z0, so we can't take this limit. Let's get the derivative of this function. Well, we can use the quotient rule here. We don't have a constant on top, so I won't use the chain rule. We have u over v, where v is z plus I, so we have v z plus I times du dz. Let's differentiate z to get 1, minus u, which is z, times the derivative of z plus I, which is 1, all over v squared, where v is z plus I. We could also take the derivative by writing our function like this here and use the product rule. So we take the first function, which is z, multiply by the derivative of the second function, which by the chain rule is this here, times the derivative of what's inside. Well, that's just 1. So then we take the derivative of this function here, which is 1, and multiply it by the second function, z plus I to the power of minus 1. So rewriting it like this and getting a common denominator, we end up with I over z plus I squared. So that's the derivative of f with respect to z, and we want to calculate that derivative at 2i. So we get 2i plus 1i is 3i. 3i times 3i is 9i squared, which is minus 9. So we get minus 1/9 i. Here is an example of a function that is not analytic anywhere in the complex plane. So f of z equals z bar. Let's take an arbitrary point z0. We have to calculate this quotient in order to get the derivative of the function f at z0. So z0 is our arbitrary complex number. Let's say it's x0 plus I y0, and we need to add onto it this small increment delta z. So that's a small increment delta x for the real part and a small increment delta y for the imaginary part. So delta x and delta y can be any numbers we like. Usually they are very small numbers. They can be positive or negative. So let's suppose z0 is here. Well, delta x could be positive and I times delta y could be pointing up the way. I won't say it's positive because we're dealing with a complex quantity. So then this point here would be our z0 plus delta z. But of course I could have put this point z0 plus delta z anywhere close to z0. I could have put it down here or over here, in which case delta x would be negative, or I could have made delta y negative, whatever. So if we do this, we get x0 plus delta x plus I times y0 plus delta y. So to get the value of the function at this point, we just change the sign of the imaginary part, because our function is f of z equals z bar. We have to subtract f of z naught. Well, z naught is x naught plus I y naught, and f of z naught is got by changing the sign of the imaginary part. So we go from x naught plus I y naught to x naught minus I y naught. So we see that the x naughts cancel out. Here we have minus I y naught, and over here we have plus I y naught. So the I y naughts cancel out. So we're left with delta x minus I delta y on top. And delta z, as we know, is delta x plus I delta y. Now we have to take the limit as delta z tends towards 0 of r. That is the limit of this thing here. But if delta z goes to 0, that's just the same thing as setting delta x to 0, or taking the limit as delta x goes to 0 and as delta y goes to 0. Okay, so if delta z goes to 0, obviously we want both of these to go to 0. The real part and the imaginary part have to go to 0 if we want the whole thing to go to 0. We can take this limit in two ways. We can imagine that z is approaching z naught along a path that's parallel to the x-axis. If that's the case, the difference between these complex numbers z and z naught is, well, we know it's delta x plus I delta y in general, but if z and z naught are on a line parallel to the x-axis, then delta y, the difference in the y values, or the difference in the imaginary values of these two complex numbers, is 0. So in that situation, this quotient here is delta x divided by delta x, which is 1. And when we take the limit of a constant, we just get the constant. So the entire limit is going to be 1 if we're taking the limit along this path here. But you see, we'll get a different answer if we use this path. So imagine z is on this path here as parallel to the y-axis. Then we can see that z minus z naught is going to be I delta y, because the difference in the x values of these 2 points is 0, or the difference in the real values of these 2 points is 0. So in that situation, these delta x's go out and we get a different result for the limit. We get minus 1. So the limit depends on which path we take, and we stated in a previous video that if that's the case, then the limit does not exist. We say that this limit does not exist. So the derivative of the function at any point z0 does not exist. So I stress that we used any point z0 here, where z0 is x0 plus iy0. So if the function is not differentiable at any point, obviously it's not analytic at any point, because for it to be analytic it has to be differentiable. Well, for it to be analytic at a particular point, it's got to be differentiable in a neighbourhood about that point.